right, ladies and gentlemen, boys and girls, today we're going to talk about the motion of circulating objects. First, we're going to pull a lot of things that we know. We'll start with some of the things that we already know, some of the equations that we know that we can use, um, and then we will talk about going in a circular motion, and then we'll apply some of the things we know and add to the concepts that we know about angular momentum and the conservation of angular momentum to uh, elliptical motion. All right, when we don't have a perfect circle or where the radius changes of this right here. So let's talk about what we have right here, all right? So when we talked about what's going to begin here, we're going to talk about, let's say we have the Earth here in the center here, and we have a satellite that's moving around that object. Let's say as it is, let's do this in terms of circular motion. So if we're in circular motion, I know that I have a radius r that is acting right there. And that radius is the same here as it is here, as it is here, as it is here. So it is not changing. All right. Since it is not changing, all right, and let's say that we know, sorry, and we also say we know that it has a certain velocity vector that's acting in that direction. All right. So we have that one right there. And there's only one thing that's acting on that satellite right now that's causing that circular motion. We know from when we talked about centripetal force that we have to have some sort of force that's causing it to accelerate towards the center, right? Instead of just going in a straight line, it's being pulled back in. And we know the only thing that's acting on this way right now is acting that way, and that is the force of the gravity caused by the Earth pulling on it. At the same time, the satellite is pulling up on the Earth, but we're going to focus on this one right here. All right, so we have it going, or the velocity vector acting this way. We have the force vector acting towards the center, and that force vector is acting along the same path as that radius. So as we start going through here, now we know that, okay, let's think about what we have here. We have our velocity that's acting here, which means we're going to have kinetic energy. We know that kinetic energy is going to be 1/2 mv squared, right? And as we're doing this outside in kind of a larger situation here, we're not doing this as a local gravitational, local being like on a near the surface of a planet or on Earth. We're going to be using universal gravitational potential energy, right? Which is going to be that negative g times the two masses divided by r. A couple things just to remind you about that. The reason why it is negative is because it is as that radius is approaching infinity. Right, that causes that to be a negative sign. The big focus that g is being a constant. We have the mass of the two objects, and then we have the radial distance, that radial distance between the two objects, which is going to be really important here today because if we're talking about objects that are not a circle, we're going to talk about what that means. So we have these different things here. So let's talk about what we have here in terms of our total energy, right? In terms of our total energy. So to begin here, let's talk about that or about that energy as we go here. So we have our satellite Earth system, right? We have our satellite Earth system, that force that's acting between them. And so we have the forces, or we're going to have our gravitational potential energy, and we're going to have our kinetic energy as they act through those. Now we know that since that gravitational potential energy is going to be based off of that R value, we have at this point right here, we have a certain amount of gravitational potential energy. And I just in the negative, it's just going below because of that negative sign. All right, because it is as it's trying to go in towards infinity there. And we have a velocity vector, which means we're going to have some sort of kinetic energy as well. All right. So let's think about this as it goes around, right? As our satellite goes around, and let's say it gets to this point right here. Right? As it goes around right here, I know my picture's not perfect, but now we start getting that same R value. Right? If we have that same R value, all right, let's think about this. As we're thinking about it, R has not changed as it goes from here to here. That R value has not changed. right? Since that R value has not changed, the masses between the two masses of the objects haven't changed, and that G force is, or that G value is a constant. This gravitational potential energy does not change. So as we notice here, we have as it starts moving around in this circular motion here, we have a constant radius, right? Because we have that constant value, we know that we are going to then have a constant gravitational potential energy. We know that we're going to have that constant gravitational potential energy, which means this is not going to change. If this is not going to change, then that means that kinetic energy is not going to change, right? Because of that, we're going to have the same or we're going to have a constant kinetic energy. And we know that kinetic energy is related to that velocity vector squared, all right? And since that kinetic energy is not changing, we are going to be having a constant speed right here. It is going to be going at the same speed as it was before, and so we have it going at a constant speed as it goes around. Since it's going at that constant speed, there's been no change in our energy, which means there's obviously no work being done, which makes sense. If this is our system, our satellite Earth system, right now there's no other forces acting outside that system. The only force that's acting right now is that force of gravity. It is between the two objects within our system. No work is done, no change in energy of the system. So it is staying exactly the same. So as we go through that here, now, what we talked about when we talked about earlier is, okay, well, now that we know this, right, we know what with the energy we're starting with. One kind of side topic that we talked about this when we first discussed this was this concept of escape velocity. What if I want to get to a point where we can't see, where we're no longer within the grasp of the force of Earth? Right? So we talked about this idea of escape velocity. What if I can get to the point, and I'm going to go this pretty briefly here. What if I can get to the point where the total energy is not going to be the same? So the idea is, if I start here and I move far enough away, essentially as R goes to infinity, can I get to the point where the final kinetic energy between the two energies between those two things are not the same, right? So where we have the gravitational potential energy plus the kinetic energy, the initials, right? Can I get to a point where I make that equal to zero, or gravitational potential energy because R is going to infinity, and kinetic energy where that object is not having an effect on the motion of the object? So let's say I want to take a rocket or shoot a cannon, I want to blast it, and I want it to get out of the Earth field where it's not going to have that conservation of energy anymore. So we know that this would be negative G mmR plus 1/2 initial velocity squared is equal to 0. We want to know how fast do we need to go to make that happen. We can rearrange our variables here, and we get our initial velocity we need to escape that gravitational field. Ends up being, I have it written on the other side over there, 2gm over r, where that r is a very important factor for us to get there. All right. What is that initial value as we go there? That initial value, how close we are at the beginning, and how much the mass is of those objects. That's the amount of velocity we need, initial velocity we need to kinetic energy to be able to pull that R value essentially to infinity. So now I want to talk a little bit about how this ties into some of the other things we talked about in terms of the forces and the angular momentum. All right. So now we tied that. This is a lot of what we've already done. All right, so now let's tie this a little bit into what we're doing right now, talking about angular momentum. So we have our object here. It's rotating at a constant velocity. It's going at a constant velocity because that R value is not changing, which means none of this or potential energy is becoming kinetic energy, right? As it's going around there, right? As it's moving around, if I'm just looking at the forces that are acting there, right? Now remember, this is a velocity vector, right? The only force that's acting on there right there is that force of gravity. That force of gravity is not creating a torque. Notice there's only one force that's acting in this situation, and it is acting in the same direction as the radius. We know for there to be a change in angular momentum, we need a torque to be acting on it. To have an impulse or a change in angular momentum, we need to have a torque acting on that object. Torque is based off the radius times the perpendicular force to that radius. So that radius is moving is between the satellite and the Earth. The force's gravity is a parallel force. So since I have here, all right, just kind of marking that off. All right, since I have here I have no torque acting on this system here, right? I have no torque because the radius is acting parallel to the force of gravity. That means that torque is equal to 0. If that torque is equal to 0, then that means that the change in the torque is equal to 0. Then that means that the change in the angular momentum is going to be 0, right? Just plugging that in right there. These are parallel. This would be essentially the sine of 180. The sine of 180 is 0. Since this is 0, we have that change in angular momentum is going to be 0, which means we know that that angular momentum is going to be conserved. So as it goes around, that velocity is going to be the same. And we can see it and we're going to do this in a moment with another example here, but that number at the beginning, right, which means the angular momentum at the beginning is going to be equal to the angular momentum at the end because it is going to be conserved, right? That means MVR, this is 90 degrees, or not, MVR is going to be equal to MVR. So whatever the mass and the radius is here, mass times radius times velocity here is going to be equal to the mass times the radius to the velocity here, right? So that's what we see for in terms of circular motion. So let's take a lot of the things that we just talked about just here right now, and let's talk about it in terms of elliptical motion, where it is not where the radial distance is not the same all the way around. So I'm going to pause it, kind of reset this right here, and I'm going to kind of reset the board to do this next part. Okay, so I reset the board a little bit here. We're going to change the situation a little bit. All right, so we still have an object, we still have a satellite orbiting the Earth here, right? But this time what it's doing is a very elliptical. I made it very dramatic here just to make sure I make a point here. All right, I have very elliptical orbit here. All right, so now we're talking about this in terms of elliptical orbits. We have essentially the same situation, and I have what I call position A and position B. More specifically, this would be the perihelion, and this would be the aphelion. All right, those are their official names. The points furthest away from the that would be for if the sun was at the center. All right. So what we have here is we have kind of the same situation. We have object going rotating. Let's say it's going rotating clockwise as it goes around from point A to point B, back to point A, right? And we have a lot of the same situations. We still have, in this case here, a force of gravity that's acting towards the center here. All right. In this case here, now that gravitational pull is going to be that force of gravity. It's the only force that's acting on this here. It's acting as the centripetal force here as it goes around. But on one side here, we'll call that distance is r. And here we're going to say the other side, all the way far away, the distance is 3r. All right, so let's think about what we have here. Let's just focus at point A right here. Let's think about what we have. All right, here we have it at a certain r value, right, which means we have a certain r value, which means we have a certain amount of potential energy. It is also going to be moving, so I'm going to have some kinetic energy here. All right. And so we have it moving at a certain amount, right? And we're going to say it's going to keep moving kind of in this direction here, right? As it goes around, we're going to have a certain amount of kinetic energy caused by that velocity that's acting there. So when I draw my bar chart here, we have a kind of a smaller radius here, so we have a certain amount. Let's do in blocks this time because we're going to compare. All right. We say have one block there, and let's just say we have 3 blocks. Oops. 3 blocks of kinetic energy for a total of 5 blocks of energy here. All right. Let's talk about what happens when it goes from, say, here, and then let's compare it to right here. All right. When we compare those two different things as it goes from one place to the other. Okay, let's set this up a little bit about how we talked about what we see here at this point in terms of the forces acting on this here, right? So what we have here is we know that torque is created, that's on any kind of system. In this case here, the satellite Earth system is created by a perpendicular force. Once again, as this moving object is going around, there's only one force acting on it, and how it compares to its radius, right, is going to be equal to that, also known as we could also rewrite it as the force sine theta. The sign here would be 0, or you could say 180. Either way, it's going to be 0. And either way, in this case right here, there is no perpendicular force, right? There's no perpendicular force. If there's no perpendicular force, then that means that the torque in this case is equal to 0. If there's no torque, if the torque is equal to 0, then that means that there is no change in angular momentum, right? That change in angular momentum is going to be equal to 0, which means momentum is going to be conserved. Momentum is going to be conserved. All right. So that means at every single point here, angular momentum is going to be the same, because at no matter what point we are at here, either here, or we'll do another moment here, like one here, the moment that there is not a torque that's acting in that situation. There's not a torque causing in that situation at those 2 points right here. So now the question is, okay, if there's no torque there, what does that mean? That means in this case right here that the angular momentum at A is going to be equal to the angular momentum at B. All right. So we look at here, okay, angular momentum. Since we're going around an object, a different center of mass here, or different point of rotation outside the two objects, outside the satellite, I'm going to use my MRV sine theta. Sorry, I just realized it's a little bit off the screen. All right, a little bit off the screen. There we go. All right, we have our MRV sine theta, which means, and in each one of these cases right here, that theta is going to be 90 degrees. So theta is essentially going to be 1. Or sorry, the sine theta is going to be 1. So I know right here that the mass of the object times the velocity of that object at point A times that radius at A is going to be equal to the mass of that object, the velocity at B times the radius at B. Okay, so hopefully that kind of rang a little bell when as soon as I wrote that one, looking at that right here, rang a little bit of a bell here. Okay, this is not the same. They do not have the same R value. This value right here is actually 3R. It's 3 times as much as in this one here. So this one's going to be the same. Mass is not changing. At A, the value is R, which means the only thing else that can be changing here is this has to be going 3 times as fast as this spot right here to be doing that, to make these values equal, right? Mass is going to stay the same, right? That's going to stay the same. R values here, we have 3R here, right? Which means to make these equal, this has to actually be going slower. at B is going slower than at A. So I'm going to draw my velocity vector there, but I'm going to draw it a lot smaller. Again, it's going slower, but angular momentum is conserved. It's conserved because there's no torque acting on it, right? And so we're trying to find out, or those two values are going to be the same, just as we break them down here, right? So what does that look like in terms of our change in our energy? Well, here, wow, okay, we have a change in, let's do in green here, we have a change in velocity. We have a change in velocity, right? It was going faster, now it's going slower. All right, if we have a change in velocity, then that means we have a change in kinetic energy. Remember, we know that the relationship between kinetic energy and velocity is, kinetic energy is dependent as v squared, all right? Which means if we have a change in kinetic energy, we could look at that back up here, right? We had the velocity as it was A, we had 3 blocks because it was going really fast. That means down here it's probably going to have less blocks. There's no work being done on the system here. There's nothing no other force acting outside the satellite system, which is I have 5 blocks here. I have 1 block here, which means most of that energy is turned into gravitational potential energy, which makes sense because it's going further and further away. Now, remember, it's getting more and more negative because of that negative sign right there, as it is getting more and more. As it gets closer, more of that potential energy starts becoming more kinetic energy. It starts becoming more kinetic energy, and then it goes around. Now, that wasn't the case. This wasn't the case. These were the same when we did circular motion because the R value wasn't the same. And here we have a different R value. Because we have a different R value, we're going to have different velocity vectors, right? Even though there's still no torque in there, we know that angular momentum is going to be conserved. Okay, this is already kind of going on a long enough video here, just kind of summarizing a lot of the different things that we see here. Most of the stuff is nothing is really new. It's just applying it to a new situation and bringing back some of our old friends here, talking about escape velocity and universal gravitational potential energy, and bringing it, introducing it to our and some old friends like the bar charts, but then introducing it to some of our new friends, talking about torque, change in angular momentum or impulse, and using our angular momentum to talk about that. Okay, so thank you very much for watching. If there's any questions, make sure to come and ask. All right, have a good day.